the discovery of radioactivity was just the beginning. As scientists probed deeper into its mysteries, they unraveled the hidden structure of the atom itself. From Marie Curie's generosity in sharing radium to Ernest Rutherford's groundbreaking experiments, the early 20th century saw rapid advancements in our understanding of radiation. These discoveries not only revealed new elements, but also reshaped atomic theory. In this episode, we explore how Rutherford and his collaborators deciphered the nature of radioactive emissions, uncovered the atomic nucleus, and ultimately paved the way for modern nuclear physics. Welcome to the Physics Frontier, where we explore the origins, evolution. Let's begin. Radium is an extremely rare and highly radioactive element with a level of radioactivity millions of times greater than uranium. This extraordinary property made radium an ideal substance for studying radioactivity in its early days. At that time, the total amount of radium available worldwide was less than half an ounce, much of which was in the possession of Marie Curie. Driven by a spirit of generosity, Curie distributed small parcels of radium to researchers worldwide who were studying radioactivity. One of the recipients of this precious radium was Ernest Rutherford, who had moved from England's Cavendish Laboratory to the Physical Laboratory of McGill University in Canada. Using the small amount of radium provided by Curie, Rutherford began investigating radioactive emissions. He noticed that radiation emitted by radioactive substances could penetrate solid objects and ionize surrounding gases. Through careful observation, Rutherford discovered that the radiation was not uniform, but a combination of different types of rays. To delve deeper, Rutherford subjected the radiation to a powerful magnetic field and analyzed its trajectory. He identified three distinct types of rays: one that remained unaffected by the magnetic field, traveling straight through, and two others that were deflected in opposite directions. Rutherford named these rays alpha rays, beta rays, and gamma rays. Alpha rays are positively charged with low penetration power. They could be stopped by a thin sheet of paper. Analysis revealed these to be charged helium nuclei. In this case, alpha particles are emitted from the atom, so this process is called alpha decay. Beta rays are negatively charged with higher penetration power than alpha rays. They could be blocked by a few millimeters of aluminum. Similarly, beta particles are emitted from within the atom, so this process is called beta decay. Gamma ray is highly powerful and penetrating radiation, requiring dense, thick lead sheets to stop them. At the time, the atomic structure was largely unknown, apart from J.J. Thomson's plum pudding model, which many scientists doubted. The discovery of radioactivity revealed that atoms were composed of smaller components, but why would an atom spontaneously emit radiation and begin to disintegrate? What were the patterns behind such emissions? These questions perplexed Rutherford, who tirelessly searched for answers in his laboratory. Rutherford later collaborated with Soddy, a young chemistry instructor at McGill University. Together, they observed that radioactive substances decayed in a predictable manner, transforming into other elements over time. They demonstrated that the rate of decay of a radioactive element was directly proportional to the number of atoms of that element present at any given time. This exponential decay relationship became known as the Rutherford-Soddy law of radioactive decay. During his experiments, Rutherford noticed that alpha particles scattered unpredictably after radioactive decay, making them difficult to study. Moving to Manchester in England, Rutherford enlisted two of his students, Hans Geiger and Ernest Marsden, to conduct an experiment in 1908. Their task was to observe how alpha particles scattered when they hit a thin metal foil. Geiger and Marsden found that most alpha particles passed through the foil with minimal deflection, but astonishingly, About 1 in every 8,000 particles rebounded almost directly backward. This unexpected result shocked the young scientists and Rutherford alike. Repeated experiments confirmed the findings. In 1911, Rutherford proposed the nuclear model of the atom, suggesting that all positive charge and most of the atom's mass were concentrated in a small, dense nucleus, while negatively charged electrons orbited this nucleus. I have discussed Rutherford's nuclear model in detail in a previous video. Rutherford and Soddy understood that radioactivity could transform one element into another, but the exact nature of these transformations was unclear. In 1913, two chemists, Geiger-Marsden and Rutherford-Soddy, provided clarity. Soddy had by then joined the University of Glasgow as a professor of chemistry. They demonstrated that when an element undergoes alpha decay, it moves 2 places down in Mendeleev's periodic table. In beta decay, the resulting element retains the same atomic mass but moves 1 place up in the periodic table. This discovery became known as the Soddy-Fajans displacement law. The same year, Soddy discovered radioisotopes, elements with identical chemical properties but different atomic masses. He received the 1921 Nobel Prize in Chemistry for this groundbreaking work. During this period, the periodic table was organized by atomic mass, as scientists were unaware of protons. The term atomic number simply indicated the element's position in the table. Scientists also had no knowledge of the positively charged particles in the nucleus. 8 years after proposing the nuclear model, Rutherford finally identified these particles. By bombarding nitrogen gas with powerful alpha particles, he observed that nitrogen atoms transformed into oxygen atoms, emitting positively charged particles detected by his instruments. Rutherford demonstrated that these particles were ionized hydrogen atoms and concluded that they were a fundamental part of nitrogen atoms. He named them protons, particles with a charge equal in magnitude but opposite to that of an electron. Rutherford's discoveries not only revealed the atom's inner workings but also laid the foundation for modern atomic physics. His groundbreaking experiments and insights continue to shape our understanding of matter to this day. Stay tuned for more explorations into the world of physics. If you enjoyed this episode, don't forget to like, share, and subscribe to the Physics Frontier. See you in the next one.